Hello everyone, how's it going? So in this video, we are going to be covering electrophilic aromatic substitution. All right, so let's go ahead, let's jump in and get on started. Now, for these videos, it's going to be one giant document, but it's going to be broken up into 3 separate videos because this is just a bulky topic. Like we spend an entire week on it in the course. It's very big and it's also very important because this topic will follow you throughout the rest of the semester. So you definitely want to make sure that you have a good understanding of it. So the first thing we're going to talk about is just kind of the reactions. Now, in a video from 2 weeks ago, we had covered electron donating and electron withdrawing groups. Okay, and this is where all of that knowledge really comes into play in a major way. So we want to understand donating and withdrawing groups. We also want to understand the terminology that comes along with this section. So not only do we have donating groups, but we also refer to our donating groups as activators. And we refer to our withdrawing groups as deactivators. Okay, so this is just important info to have when you're trying to do these kinds of problems. Now, donating groups, what they do is they increase the rate of the reaction. And for withdrawing groups, they decrease the rate of the reaction. So when we're doing electrophilic aromatic substitution, it's commonly abbreviated as EAS, because it's just a mouthful. When we're doing these reactions, you prefer donating groups. You're going to have something called directors, and you're going to have to determine who's in charge. Well, donating groups will always want to be in charge over withdrawing groups, okay? And down here, I just have how to make an acid chloride. This is a little review for you from Orgo 1. This is a reaction that commonly pops up in this chapter. So it's just something I wanted to throw in there and make sure we were all clear on. So acid chloride, you use SOCl2, and it turns your OH to a Cl, okay? All right. So now we're going to talk a little bit about the directors. So there are 3 kinds of positions available on your benzene ring. They are ortho, meta, and para, okay? Now, ortho and para directors, those are your activators and your halogens, okay? Now, halogens are an exception to the rule. Generally speaking, all donating groups are activators, and they're ortho-para directors. When we're talking about meta directors, usually we say, oh, it's all withdrawing groups, but it's actually not. So halogens are withdrawing groups, but they donate or they direct ortho-para. Okay, so they're an exception to the rule. And I just wanted to make sure that we talked about that a little bit. So ortho-para directors, those are your activators and halogens. And then your meta directors, those are your deactivators, so not including halogens. Okay. Now, when we're talking about major products, right, we say para is the major product when there is a large sterically hindered group on the benzene ring. So this is usually like an isopropyl, or you could do just a regular propyl, right, a 3-carbon chain. Generally speaking, the only group that really directs ortho first is going to be a methyl group. Other than that, between your ortho and para directors, you're going to be going para majority of the time as the major product, okay? It's just that when it comes to methyl groups, we don't really go para first, we go ortho first, okay? All right, when you have 2 or more groups on a benzene ring, you want to be mindful of steric hindrance. So if a lot of interactions can occur, then it's not really the best place to put that group, okay? And we're going to see examples of this as we go throughout the problems. Now, the next thing I want to talk about is when you have withdrawing groups on a benzene ring, right? We say that the ring is deactivated. When you have a withdrawing group, it means that you can't really do any more Friedel-Crafts reactions, okay? All right, so that's just some info. I know you don't know much of the terminology yet, but that's the point of this video, to kind of get you familiar with everything, okay? All right, so this guy on top here, this that I have circled in red, that red laser, this is going to be what's provided for you on your cover page, most likely. And this is a nice list for you. So this is super convenient. It tells you who all your ortho-para directors are, and it tells you who all your meta directors are, okay? Now, before your exam, they always upload the cover page. So just wait for that announcement and then look at your cover page. This should be on there as well as all of the reactions. Okay, so that'll save you some card space. All right. The next thing I want to talk about is most reactive and least reactive, right? So we have a bunch of groups here. We have strongly activating, moderately activating, weakly deactivating, right? So on and so forth. So when we're arranging these, we can say that the most reactive, or who makes our benzene ring the most reactive, are your activating groups, okay? More specifically, strongly activating is preferred over moderately activating, preferred over weakly activating. And the one that I didn't get to include here is just a plain old benzene ring. So a plain old benzene ring with no groups on it goes right here. So it's kind of that divider between activating and deactivating, okay? All right. Now, as far as who wants to be in charge, deactivating groups, they don't want to be in charge, right? They make the ring less reactive. That's not what we want. We want something to make the ring more reactive. So the more activating you are, the more you want to be in charge, okay? And this will all make sense when we do problems. It's just a lot of jargon to get through. All right. Over here, I have your benzene ring, okay? I have it labeled. So the R group is any random carbon chain, okay? Any kind of group. It could be any one of these, okay? So that's what R stands for. Now, ortho. Ortho is your 1-2 position. When we say 1-2 position, we mean starting at the R group, you go 1, 2. So 1-2 is always ortho, okay? Meta is always 1-3, 1, 2, 3. And para is always 1-4, 1, 2, 3, 4. Now this holds true no matter where your R group is. So if you have a ring and your R group is over here now, right? This is 1, 2, this is ortho. 1, 2, 3, this is meta. And then that would be para. Okay, so it's all based around the group, your director, the person who's in charge. Okay, all right. So I think that's everything that I wanted to cover on this slide. So the first topic we're going to go and dive into is reactions. So as you can see, there are a lot of reactions here that you are responsible for. So what I plan to do in this video is cover all of these reactions, break them down, show you all the mechanisms that you need to know to continue forward, and then we're going to apply them to some questions and really figure out how to do this in the best approach, okay? All right, so let's go ahead and let's get started on some of these reactions, okay? All right, so electrophilic aromatic substitution. The first thing I want to do is just talk to you about the general reaction mechanism, okay? So you guys remember the terminology nucleophile and electrophile. So when something is a nucleophile, right, with an N, nucleophile, it goes ahead and it does the attack, okay? When something is an electrophile with an E, it wants to get attacked. So here, this E plus is representing our electrophile, okay? And in these cases, our benzene ring, they act as the nucleophile. They're the ones that do the attack. So any of these double bonds can attack. I'm going to use this one right here. So this is going to come on out and grab that E, okay, that electrophile. When this happens, we're breaking the benzene ring, right? Hopefully you remembered from your aromaticity chapter that a benzene ring is an aromatic compound, right? So what does that mean? Well, that means it's super stable, okay? So it doesn't necessarily